Thanks everyone for coming. Yeah, I think no need to much of an introduction. There's going to be quite a lot to get through today, so I'm going to try and whiz through as fast as possible. I'm going to make some assumptions that for this talk, you're probably going to already know JUCE. You're probably already using it. It's about optimizing JUCE. If you're not very familiar, there's going to be a few things you'd need to catch up on beforehand, so just keep that in mind as I go through. If we're going to talk about measuring performance, if we're going to talk about performance, we need to talk about measuring performance. So let's do just a quick whiz through. First of all, if you're doing something in JUCE and you're hitting some performance issue, a good first place to check is the demo runner. So we're going to be looking at the demo runner quite a bit today. This is the demo runner running just here. For UI stuff, you would just browse to demos, go to GUI. There's a whole load of different demos that you could use. I know most people in the room probably already know this, but just worth reiterating. If you're doing something, double check if we're already doing it in the demo runner and see if there's any obvious differences between what you're doing and what we're doing. That might give us some indication of where there could be an issue. But that's not going to tell you enough, really. So one of the first things you might learn is something like the JUCE enable repaint debugging. It's useful for some stuff. You can turn this flag on, build your project, and everywhere that you're repainting, you'll see like a randomized color, slightly transparent, laid over the area that's being repainted. But you're not going to know how long it took. If you've got a component on top of another component, you don't know really which one was causing the painting. You don't know why that one's being repainted. And there are cases where you could actually be calling paint, which we'll look at later, and you won't see the color rectangle on the screen. So it doesn't always tell you everything. It's a good first step. One of the most common problems is that people are just repainting stuff when they don't need to. Another common one that you'll see a lot of, and I used to use this a lot, is something called Quartz Debug. So this is macOS only, and this is part of the Xcode additional tools. I would first warn that if you have epilepsy, don't use this tool. Extremely bright, very fast flashes on the screen. But for the most part, in modern versions of macOS, you'll normally just see it just painting the whole rectangle of the UI, which isn't very useful for trying to figure out exactly what's painting. And again, we can talk about that a bit later. If you just want to measure how long something took, there are a couple of tools already in JUCE. They're quite useful for quick debugging. There's scope time measurement. I haven't tested that code, so don't tell me if I have got a problem with it. But the basic idea here is you have a double, you pass it into the scope time measurement over some scope, and you'll get the timeout in seconds. One step up from that, we also have something called the performance counter. Again, it's quite useful. Here we're making a performance counter that after every 1,000 times that we've done some measurement, we've done a start and a stop, it will print something out. You can also pass a file to it so it can log to a file. It's useful for some quick debugging on small areas, but trying to get a grasp of your whole UI and where things are happening, I don't think it's quite so useful. So for that kind of thing, we need to start talking about profilers. So if you're on macOS, then Instruments comes with Xcode. It's a very useful tool. I've given some links to a few talks up here if you haven't watched them from WWDC. The most obvious one that most people turn to initially is the time profiler. It's very good. It takes a lot of samples of your code. It gives you a good idea of where the hot paths are within your code. And normally it gives you a pretty good idea of where you're causing issues. But you might see certain things come up and it's still not completely obvious why. Maybe it's not even very obvious exactly which component it's happening in, because you might just be in a tree of calls and it's not always obvious exactly which component is the one that's triggering those problems. Another thing you can add to this, I should say, is something called the OS signpost. I'm not going to go into it today, but it's a bit like the scope time measurement. There's ways in which you can call like a kind of start and end to measure some period of time, and you can add an instrument called the signpost or OS signpost, and then you can see more details about that specific timing. In a similar vein, Visual Studio also has a profiler built in. Again, allows you to see the hot paths. And in a similar way, there's event tracing. I haven't used it extensively, but it's another way in which you can go and put some instruments into your code in order to measure particular points. One that I only got introduced to the other day, so shout out to Attila on the JUCE team for showing me this one. And I would like to really quickly show this because I'm actually quite excited about this profiler. It's free and open source. There's a great video of this from CPPCon, and they have an interactive demo, although maybe, no, yeah, it's going to load. I think we're okay. And there's a lot of stuff in here that's very useful. It looks like it actually captures the frames so you can see them drawing. Oh, we've got them mirroring still, yeah. I don't know why it's showing up on the screen. I'll move that out of the way. And you can dive into things like memory allocations, CPU load. If we go into like messages, there's stuff here. You can get statistics on certain areas. It looks like it could be a really useful tool. I haven't used it extensively, but I'm quite excited to try it out because I think it would be really useful to track things. As I understand it, this is used quite a lot in the gaming world. So maybe it's something we could look to adopt more in the audio world. I haven't heard many people using it yet. So that's something I'm looking forward to trying at least. Let me go back to my slides. Another popular one is Perfetto, and Sadara has made if anyone knows Sadara, has made a JUCE module with a melatonin Perfetto that makes this integration quite easy for JUCE projects. There's a link there again if you want to go and read the blog about that. This is some examples of what that looks like. You can kind of see examples there of being able to measure specifically your paint calls, your audio callbacks, seeing how that interacts. And then another tool from Sadara as well is the melatonin inspector. I know a lot of people have been using this, and it's a very useful tool, not just for measuring performance. It does have some stuff for that, but also for just seeing your whole component hierarchy, for being able to adjust certain things, to get a feel for how you could do certain changes without having to always just change the code, so you can kind of get some ideas early on, and useful for like accessibility, a bit like something like the Accessibility Inspector or Accessibility Insights, I think it is on Windows. So again, some examples of that. And you can see it has got some measurements of our painting, but we're exploring just a moment that does miss some of the details about the painting routine. It's looking at how long you spent in your paint function inside your component, but there's a lot more to put in a component on the screen than just the paint function. So we're planning to introduce something that I'm calling the component diagnostics. And this is going to be a way to get a bit more information out of your components in order to make some more diagnostics about exactly what they're doing and how that might be impacting the rest of your program. So I'm going to give you a quick example of some of that. He says he is. Yeah. So on this first screen here, this is just an example to try and show a couple of different callbacks that you get. So the main things you get is you get a measurement for your paint call, you get a measurement for your paint over children, and you get one for apply effect. So if you've set an effect on a component, then there's a user function that you would normally implement. Certainly for the custom effect that you've applied, then there'll be an apply effect. And you'll see in the graph at the bottom here, it's quite noisy on this display. It's actually less noisy on the laptop, but some of the other demos we'll see in a second aren't quite so noisy. Then we've got the amount of time in yellow is the paint. On top of that, we've got the orange, which is the paint over children. On top again, the apply effect, and then everything that's red is basically all the stuff in between. It's all the stuff that wasn't your user code. It'd be the stuff in JUCE, and there could be various things going on there. And it's useful to know that the things you call on a component, the effect they might have on those aspects of it. So in this, we're going to have a few components that we're going to look at a fair bit to play around with them and do different things with them. So we've got a cheap component here. So all this is doing is just drawing a rectangle. You can see that this is taking, on this screen, about 8 microseconds, 7 microseconds. Most of that time is in Paint, a little bit of time doing some other stuff in JUCE. And then we've got an expensive component, something that's drawing a radial gradient. It's drawing some text, it's blurring all of that, and then it's drawing some more text, because why not? That's going to be nice and expensive in JUCE. It's the kind of things people come up and say, hey, this is really expensive to do. So we'll look at ways in which we can maybe make that a bit faster. Another thing we'll see is like This is maybe not your typical animated component you've got on your plugin, but it's an example of having something that's changing all the time. You might have some meter going off, or you might have some parameters that are changing and they're causing some kind of animation on the screen. Something's been repainted regularly. So we're going to play with that as well. And then we've got another example here of where we've got lots of components. So we've got, I think it's 625 components laid out here, 25 by 25. Each one of these is just fill in a rectangle, just like the cheap component. And we can see here how much time is in the total time of, so the graph at the bottom is showing the total time of the paint in the yellow. You'll get individual callbacks for each of the components, and this is just summing them all together so you can see it clearly. I should also add as well that green line is the median time that you're getting over a certain period, and that's what the value that we're reading out is also telling us about. So they're the main components we're going to look at as we look through some of the ways we might tune JUCE. So let's go through. Also want to add that this component diagnostics, I think there's some cases, and we'll look at a little case at one point where you would use this yourselves, but actually it's probably good if we look as a community building some tooling around the component diagnostics and finding the right tooling. Something like melatonin inspector would be a good candidate for integrating with the component diagnostics so that you can get more valuable information over the whole thing. And sometimes there's different ways that you want to use those diagnostics. So we didn't really want to make a definite decision of the way in which you're going to measure everything. So the JUCE marketplace is due to come soon, and it might be a good place if anyone wants to make any tools to put those tools up in order to share them in the community. So let's talk about optimizations. So setPaintingIsUnclipped. This is quite a popular one. I think I probably learned about this years ago when Jules did a talk on painting at an ADC event. And clipping the context is somewhat expensive. In earlier versions of JUCE, this could be really beneficial to call this setPaintingIsUnclipped. But one of the reasons it was so beneficial then was actually because it prevented a whole load of additional clipping that would happen, that on the most recent version of JUCE, we prevent for almost all users by default. So this will get you less of a benefit than it used to, but it can still play a benefit. So we can have a quick look. So let's first just look at a cheap component, and let's do cheap unclipped. And hopefully this is steady enough that we'll be able to see it. But what you should be able to see from here is that there's not going to be much of a difference between the two of these. But if you look closely at the graph, you'll see that the amount in red on the one on the right-hand side, which is our unclipped, is less than the one on the left because we're doing less work, right? But this is just one component. So a more interesting example for this would be if we had a lot of components. So if we went to our grid and we went to grid unclipped, then we can start to see some benefits in applying that setPaintingIsUnclipped. So we can see the amount in red. The amount that JUCE is having to do is less in these cases. Previously, if you called setPaintingIsUnclipped, you would normally not be able to get another optimization that we're going to talk about next, which is setOpaque. Now, in the past, I think it's been sort of generally put forward that you should just call setOpaque on anything that is opaque. And the reason was that JUCE by default would, for every component, go and look at all the children components and the sibling components to find if any of them were opaque and then cover the particular component. That can be quite expensive when you've got a lot of components, which is why setPaintingIsUnclipped was so useful before, because it actually stopped those checks. So it meant you never got the benefit of the setOpaque when you were using setPaintingIsUnclipped. We've changed that recently so that you can still get the benefits of setOpaque, but what it means now is that when you add setOpaque, any other components will now be checking that component to see if it's covering it. There's some nuance there in terms of where they are in the component tree, but it means there is a slight cost to it. So the important thing about setOpaque would be to measure that you are getting a benefit from it. So I'm going to have some examples of that. Let's have a look. So first off, if we were to, let's just take out grid. And if we were to do a grid that where every component was setOpaque, we can see that we have some additional cost here. And the additional cost here is that, so all 625 components have been set to opaque in this example. The first component has to check the 624 remaining components to see if any of those cover it. The next one's having to check if 623 components cover it, and so on, all the way through. The interesting thing about this is the knock-on effect. So I've put this grid opaque on the left, and I've put let's just put the normal grid on the right. And if I were to swap these around, so I'm just going to put this one to the normal grid. If you watch this left-hand side when I select the grid opaque and just watch the timings, you can now see that the timings have really increased on the left-hand side. This is a very extreme example. I don't expect most people to be doing this. There's no advantage to calling set opaque here. Nothing's covering anything else. But the problem is the one on the left-hand side, all 625 components are having to check the ones on the right-hand side to see if any one of those 625 components are covering it. And in this case, they're not. So you might say, well, what's the point of setOpaque? Well, there are sometimes some useful cases for it. So if we had a non-opaque overlay, and we had the opaque overlay. So in this example, on the left-hand side, I've got a component where the overlay is not set to opaque. So all of the squares underneath it will still be drawing, and then the square on top will be drawn over the top. So this is basically our cheap component on top of our grid component, but slightly reduced in size. Whereas the one on the right, we are setting opaque on that top level component, that square, the big red square. And so a bunch of the squares don't have to draw. And so in this case, it is useful. And you should see the amount of calls on the paint, the yellow section, has gone down. And as a consequence, so has the red section, because we've actually been able to say, hey, there's a whole bunch of work we don't need to do. We don't need to go to these components. So it can be an advantage, but I would say when you're using setOpaque, measure and make sure that it's actually an advantage in your case. Make sure you're getting a benefit from it. Okay. setBufferedToImage. This is my personal favorite tool for a lot of optimizations. I should say, though, that I guess my background is predominantly in plugins, but also some apps, and predominantly Mac OS and Windows. And a lot of this is true because of the Direct2D renderer and because of Core Graphics. Some of this stuff may not be as true on certain platforms such as Linux or Android. They should be true pretty much, I think, for iOS, macOS, and Windows, though. So first of all, let's just look at what setBufferedToImage looks like. If I just took a cheap component and I buffer to image, we'll see these normalize in a minute, the graphs, but there's not normally an enormous amount of difference. In fact, normally on my laptop, these are identical. It looks like on this particular display that they're slightly different. That's worth adding as well, actually. The display you're using, or I've noticed whether my power's plugged in or how much there's a battery on my laptop will change these results. How much I'm moving my mouse will change these results. macOS seems to do some optimizations, say, oh, you're moving your mouse over there, I'll put a bit more time over there. And it seems like the efficiency of the cores go up whilst your, all the performance of the cores seems to be increased in those instances. So just keep that in mind when you're testing things, that the environment can change things quite dramatically. But you can see on the right that we're only really spending time in JUCE because we're just painting an image all the time. We're not calling your paint function anymore, whereas the one on the left, where we are still calling the paint function. So if we were to go to something like the expensive component and then do buffer to image, we're going to see a dramatic difference in the timings. So the one on the left here is taking 28 milliseconds to draw. The one on the right is taking about 3 microseconds to draw. So there's an enormous difference in the amount of time it might take to draw an image compared to having to repaint the component all the time. I guess it's worth saying that JUCE by default sort of almost treats all components as they're always invalid. It's like they always will just repaint everything. And doing set buffer to image is a way of caching your drawing. It's a caching technique. But I have noticed over the years that a lot of people get tripped up by set buffer to image. So I just want to talk a little bit about that. I think this is covered in the docs, but it still took me years to realize exactly how it worked. And I know other people who are very good JUCE senior developers who have been tripped up by this. So I thought it'd be good to get on record. So you've got your component, you've got your expensive component, and then you go and add, it's a background component, and you go and add some child to it. And that child needs to animate. Maybe it's a meter or something, or it's, like I said earlier, something that's moving around on the screen, something that's active. And you think to yourself, well, that's really expensive, that background. What I'll do is I'll just call set buffer to image on it. Anthony told me that makes things much faster. Well, what actually happens is the set buffer to image buffers not just that component, but all its child components and your paint over children function that all gets put into that set buffer to image. So it will no longer visit any of the children underneath it. It will just have that one component. But the problem is if any of those children need to be repainted, as in they invalidate that image, then the whole image needs to be repainted. Unless your child was opaque, for example, then it's going to need to repaint pretty much the whole image. There are some exceptions to that, but for the most part, I think it's surprising for a lot of people when they first do it. So the technique I tend to recommend is something I call the leaf node only drawing pattern. Maybe someone got a better name for me. It's maybe not the most catchy name, but it hopefully gets the point across. The idea is that you have really just two types of components. You have components that do drawing, and you have components that have children. So you'd make some component, and this component wouldn't implement a paint function. It wouldn't implement a paint over children. It might have a resize method so that it can resize its child components because you would add children to it. So in this case, we would add our background component as a separate component, a child component of this container component, if you like. And then we'd add our other component as another child immediately after that. And in this case, if we call setBuffer to image, we really do just set that one background to be an image. And now that image won't get invalidated when the sibling is redrawn. So we're moving from an image that contains both of those to this. And to see the effects of this, so here's what you get if you've added the animated component as a child. And if we compare that to adding a sibling, we can see what the massive difference is here in performance. And what I've seen a fair number of times, I see it on the forum too, people call set buffer to image and they say, oh, my performance is even worse than it was before, which is understandable because every single time, if you're constantly repainting, you're having to repaint that object into an image, and then you're having to paint the image to screen, which is even more work than just painting the thing in the first place. But if you've got stuff that isn't changing very much, especially stuff like text, then this can be really useful because you're kind of limited to however long it takes to take an image to draw to the screen. That's how long it's going to take to draw to the screen. So as long as things aren't changing very often, it can be a very useful way to split things up. Going to other demos, I want to do that. So as we're talking about images, it's also worth mentioning, particularly since Direct2D has been added for Windows, that if you're making temporary images in particular, so let's say you're creating some image inside of your paint method, and then you're painting something into it, and then you want to blur that image, and you're gonna put that image to the screen, and you're gonna throw that image away. Then it's good to call set backup enabled false on that image. And all that's really doing is preventing the need that images by default will, after they've gone to the GPU, there needs to be like a copy back to the CPU in order to enable a backup in case your graphics device disappears, or I think some stuff to do with displays. If you look at the docs down in I can't remember the exact class name, but if you look at the docs on the graphics context and you look at what that's calling, which is on some pixel data, you'll see there's an example of how to test for this scenario. So if you're going to call set backup enable false on something, especially something that's not temporary, then it's best to go and do some testing to make sure your UI is going to respond correctly. But generally speaking, it's going to make things faster if you disable it. You just have to watch out that it's not going to cause any problems for your end users. If you set buffer to image, it actually does this set backup enable false, and then it has like an additional check to see if, the backup's disappeared, I need to update the backup, and it creates a new version of the image. So it tries to be as efficient as possible. So you can use that as a kind of example. If you need to do images separately outside of set buffer to image, that's a good place to look. I haven't got an example of that because this really only applies at the moment to Windows, and I'm on a Mac. So another really popular one that comes up all the time is this mouthful of a preprocessor definition. The JUCE GUI graphics render with multiple paint calls. I never remember it. I always remember it in some odd order. So I think probably a lot of people in this room probably have some idea roughly what this does. And a lot of people see this and they hear about it and think, oh yeah, enable that. That should be the default, shouldn't it? That's what we should always use. So let's go over quickly what it's actually doing, and then let's look at some examples. So the classic example of this is you've got some meters on the left, your input meters, you've got some meters on the right, your output meters. You've got this expensive drawing right in the middle of your screen. And so the meters change a little bit on one side, the meters change a little bit on the other side. We just need to repaint a tiny little bit, don't we? We need to repaint these components. We let the OS know and say, hey, here's the rectangles, here's the areas that need to be repainted. And Mac OS comes back and says, yeah, no, what we actually need to paint is this whole big thing in the middle. We need everything. It would normally even be bigger than this. This is if you're trying to optimize it. It would normally take up from the top left of 1 meter down to the bottom right of the other meter. And so you basically end up repainting the whole thing every single time. And you suddenly see all of your paints are being called all the time. And you're thinking, why on earth is that? And so you turn this on and you realize, hey, this makes it perform just like it does on the other platforms. It only calls paint on my meters. That must be better, right? And it can help for sure. So let's see if we can have a look at an example. I'm going to get... So let's bring up this little demo. So we've got this plugin. It's doing exactly what we said. It's got meters on the left, got meters on the right, and it's got our expensive component in the middle, which we've already seen. We know is very expensive to draw. And I've put some basic diagnostics printed in this. I cancel that. I'm not going to cancel it. I'll probably stop my screen sharing. And so every second, I'm just reporting what's the performance of this thing. I'm basically looking at how many times of each one of my components drawn. I've just got these 3 components, right? And you can see that the average draw time is like 28 milliseconds. That's not really reasonable. We're not really going to get very good frame rate out of that. I mean, we can see these are drawn about 34, 35 times a second, but I've added nothing else to this whatsoever. So not ideal. So we might think, first thing we do is we just set that preprocessor flag. So I'm going to build here with this. Hopefully Xcode doesn't try and update in the middle of it or something. And we'll see that in a moment that we should expect now that this center area shouldn't be drawn anymore. And so we should only be drawing the left meter and the right meter. And so, our performance should improve. I think that's what we would expect. And sure enough, that's exactly what happened. That the left meter's drawing more. The left and the right meter are drawing more often than they were before. Presumably the frame rate of this display is probably about 50 hertz. If I'm running this on my laptop, it's 120. It will run at 120. And we can see there we're taking much less time, like about 170 microseconds or something like that. So that's great. That's fantastic. And a lot of people turn it on, and that's good enough, and that will work for them. But if you maybe remember what I said about an expensive component, I said that you could call setBufferedToImage on it. So what about if we just try for a little test? We go back to the one we had before, but we call setBufferedToImage on it. I haven't tried this on this display, by the way, so I don't actually know this will work. The other thing, I'm building release builds here, right? Because if you're going to be profiling your UIs, sure, you want your debug builds to work well enough that you can use them, but your users are going to be using your release builds. So I think it's important to measure your release builds, generally speaking. And we should see here that now everything is drawing, and it's drawing at the 50 times a second. But now look at how short the time is. Now we're talking under 50 microseconds. So that's quite a speed up, and in some cases it can be more than that. It's about 10 times speed up on my machine. So you can get better performance by having that flag off. In some cases, it's really dependent on your UI and how much work you want to put in. It might be more work. It may be that turning that flag on is good enough, and it means you can release your product, and you're not really getting user complaints. It's fast enough. Sometimes that's all you need. But that's the reason we don't turn it on by default. Basically, the drawing can be asynchronous in the case where the flag is off, and the drawings end up being synchronous when the flag is on. So people ask, why isn't that the default? Why isn't it always on? That's the reason it's not always on. So let's go back to the talk. Transforms. Okay, so something I've seen occasionally, like people trying to change like the sizes of certain things, the heights of stuff, particularly if text is involved. We've seen people like implement zooms, for example, where they're actually recalculating the height of like text in order to zoom in and zoom around. And so if we just look at an example of what that actually does, so I've got animated font height, font transform, and we see the difference between the two. If you can spot the difference on the left and the right, I'm really impressed. You might say, well, why doesn't JUCE do this by default? Why isn't it when you change the height of a font that you just use a transform? And the problem is that if you change the height of a font, then it's possible the shape of the glyphs changes. So at smaller sizes, it may be that the shapes change so that there's less detail, so that it's more visible to the user. You can have things like emojis that would change the amount of detail that are in them, for example. So we can't know in advance whether the shapes of the glyphs are going to remain the same at different heights. And so, nor can you when you use the transform, but you can make a more informative decision on your UI on whether maybe using a transform might make more sense in your particular situation. And you can see here that it's much, much cheaper in order to use a transform than it is to animate the height. And it's worth saying as well that transforms are normally, in a lot of cases, basically free to add on a graphics context, because there's normally already one for anything like like you've got a retina display or something like that, then there's already normally a transform involved anyway, and you'll just add into the existing transform. So it doesn't normally add anything. How much time? Oh, actually quite good for time. Okay, I wasn't sure if I'd be able to get to this one so much. I've managed to speed through. Drawing text is a subject that comes up a lot. So if you do see these paint calls, I think quite often, and this is more true for modern versions of JUCE on JUCE 8, because we've added the Unicode support, and there's more things to consider when we're shaping text than there ever was before. There's things like ligatures and all sorts of extra things that come up that just weren't dealt with before necessarily on older versions of JUCE, and that does add to the cost when you're drawing. We've put a lot of things in place to try and make that it's not a burden on you. And to be honest, if you follow most of the rules already above, you're probably going to already get most of the benefits you need, because if you've already got most of your static text being drawn by an image, then you're no longer calling draw text anyway. And the only calls to draw text are on things where text is changing. And so that will really limit how much you'll see in that stuff come up in your profiler. But just to show some aspects that you might want to consider, and like, I think font rendering in general could be a whole conference, to be honest. So I'm not going to be able to dive into detail. But if we were to call something like draw fitted text, then we can see that already we're down really just a few microseconds. It's not that slow. If by comparison you made your own a GlyphArrangement object and you called add fitted text, then you can see that it's actually very expensive to shape the text. And so what's actually happening here is when you normally call something like draw fitted text or draw text or all the graphics context calls, there's some caching that's happening for certain things. If your text is changing a lot in any way, like the height, then it's having to be reshaped and then it becomes more expensive. If your text is very long, really, really bulky, you've got a lot of text, and especially if there's no like new line breaks or anything, it's just constant load of text, that will be pretty expensive to draw. But we try and put in what optimizations we can. Those optimizations are kind of global across your whole app, and we can't make certain assumptions. You might be able to make better assumptions about your text. So, these examples you can access when we release this. You'll be able to access the code examples. I wasn't going to dive into them today because I was worried about taking up too much time on the talk. But you could cache your GlyphArrangement, and you can slightly improve on the drawing of that text. So in this case, basically all it is you just have a member that is the GlyphArrangement, and every time there's something about the text change, for example, if I was to start resizing this, then we should start seeing some spikes, he says. Actually, you're not seeing very many spikes at the moment, but you will start to see slight differences when it's being reshaped, and then it will be cached, and then you've got it, because that GlyphArrangement will have all of the information it needs to have. So you wouldn't normally want to create a GlyphArrangement every single time that you're in a paint function, for example. You'd want some member, as long as you know the text isn't changing. If the text is changing, you're kind of forced to do the extra work. But in most cases, I think changing text, it's normally a short bit of text. Maybe you've got a parameter, maybe you've got a little value that's changing all the time. The shorter text, not so costly. It's when it starts to get a bit longer that it can be really costly. And we have things like the text editor, that's all been reworked for JUCE 8. That deals with a lot of these things and tries to optimize that as well. And in these tests that we share, you'll be able to go to a lot of the other tests that are in the demo runner. So you can go and look at things like a code editor and see how well it performs. You can paste a load of text in and have a look and have a play around with the performance of them. Let's go back to the slides. Yeah, so quick summary. Number one, I think if you took anything away from this talk, it would really be profile your code, right? Because like, it can be really hard to determine exactly what is causing the issue, and particularly the way that one component can have an effect on the other components. Even in that draw text example, what could happen is if you've got lots of text that's changing on your screen, and you're not, say, painting your static text to images, then even when your static text comes to draw, it might be that all the caches we're using have been exhausted by all of the changes that have been happening on other parts of your UI. And so they go, oh, my thing isn't in the cache anymore. I have to regenerate and reshape all of my my text. So by doing things like the setBufferedToImage, they won't need to go and check the cache at all, because the cache will be the image. But profiling your code is probably one of the best ways to try and figure that stuff out. And hopefully with the new diagnostics, that will make that a little bit easier. Generally speaking, if you're really confident that you're not going to paint outside the bounds of a component, then setPaintingIsUnclipped true isn't a bad idea at all. The only sort of aspect to it, I think, is a maintenance burden. If you change something about that and suddenly you are painting outside the bounds, then you've got to watch, because you could start having some little glitches or something like that on your screen. So that's the only aspect of it to warn. Only call setOpaque true if there's a measurable benefit. I forgot to mention, except on a window. So on the main window, if you know you're filling the whole window, then you should call setOpaque on the window, and that offers some improvements too. So it's a bit different for that top level component, that's the window, but for the rest of your components, make sure that it's actually providing a benefit. If a component doesn't need repainting often, and it's more expensive, the painter function is more expensive than painting an image to the screen, then setBufferedToImage could be a really good idea for you to use. You just need to make sure that you're not invalidating it in some way. So using the leaf node only method, I think, is a good way to prevent those surprises. Call set backup enable false on images that are temporary. You could call it for images that aren't temporary, but almost definitely for images that are temporary, it's a reasonable thing to do. And again, measure with the core graphics render with multiple paint call. Maybe it's good enough for you, but if you really need to home in on performance more, it might make sense to have the flag off and see if you can optimize further with it off. Consider using transforms, and you could consider using your own GlyphArrangement object in order to cache that. But I would say if you've done all the other stuff, chances are you won't need this one so much. There probably is more that we could talk about, and I'd love to talk more with you, so I'd love to ask some questions. Slides are available, so if you want links to any of those, especially those profilers or anything like that, hopefully you should be able to get to that from there. That's it. Thank you very much.